Good morning, everybody. Welcome to our virtual Zoom lecture. I hope you did the quiz. If you haven't done the quiz number 8 and quiz number 9 it is due tonight. Please take note of that. Quiz number 8 and number 9 is available online due to tonight. Midterm exam number 3 is scheduled for next this coming Tuesday. The study guide will be available tomorrow or later on today. Meanwhile, use the study guide for the quizzes to prepare for the upcoming exam, covering chapters 7, 8, and 9. Today I want to continue from where we stopped last time. All right, from where we stopped last time. Can you see my screen, please? Somebody tell me if you can see my screen. Can you see my screen? It's gonna be 7, 8, and 9. I'll send out Antonia. I'll send out the study guide. Let me see what's going on. Last time I had problem with my machines here, and it appears that you can see my screen. Let me just try one more time and see what is going on. All right, I need to grant access and you will be able to see. All right, if you get disconnected, please log in again. All right, if we get disconnected, it's telling me to restart the computer, but hopefully it will allow me. Yeah, we are in business. I think you can see. Can you see the screen right now? Can you see the screen right now? Yes, thank you. Yes, that was, you know, a little bit of concern on my end that last time we couldn't see. So everybody can see now the screen. So what you see on the screen is section 9.6. If you recall all the way to chapter 8, basic chemical bonding, we only looked at how a chemical bond in chapter 8 by the fact that, you know, a line represented a single bond, 2 lines double bond, 3 lines triple bond, and you know how many electrons are in a single line, 2 electrons and so forth. That was just basic concept of a chemical bond, how a chemical bond look like. In chapter 9, so far we have looked at one bonding theory. Apart from the molecular geometry, one bonding theory. To this point, I've covered the valence shell bonding theory. Chemists abbreviate that as PP. This stands for valence shell bonding theory. How is a bond formed? We talk about the overlap, you know, 2 s orbital overlapping, and you see how 2 electrons occupy, you know, the overlap. This is what we looked at last lecture for hydrogen gas. For hydrogen gas, the overlap is indicated by 2 spheres and where the electrons being shared occupy. In chapter 8, we only use a line, all right? Now, today, we will look at the last bonding. We will look at the last bonding theory. We call it molecular bonding theory, MP for molecular bonding theory in a different way. But before we look at that, in the upcoming section, let's relook at in details the double bond and triple bond. And I think there's a section in the lab you may be asked to look using the concept we look in 9.6. In chapter 8, you know this represent a double bond. All right, 2 lines represent double bond, and 3 lines represent triple bond, and we have 4 electrons here, and we have 6 electrons on 3 lines. Now, in 9.6, multiple bonds refers to these double and what? And double and triple bond. In double bond and triple bond, we have what we call sigma bond and pi bond. In both multiple bonds, that means triple and double bond, we have 2 types of bond in there, sigma bond. This is called a sigma bond, just a single bond. Sigma bond is simply a single bond, all right? Single bond, I know you know or you are familiar with the single bond, and we use the Greek symbol sigma. This is the way you know sigma. This is represent a single bond, and pi bond represent a double bond here. This is pi bond using the Greek symbol pi bond. The pi, of course, you know what that means. So when you look at the multiple bond, we will be talking along these 2 terms you see down there, that what constitute, or when we say a pi bond, what should come to your mind? A single bond. When we say pi bond, what comes to your mind? Let's see. In sigma bond, which is a single bond, there is an overlap of head-to-head, all right? And the shared electron will reside in this region of the overlap. So if this is a p orbital which look like a dumbbell, this is a p orbital which look like a dumbbell, they overlap in head-to-head to form a single bond we call sigma bond, single bond. This morning I was looking at the question, and some of the question was asking about, describing, sigma or single bond. How do you describe that? Head to head, is it head to head or side to side? You have to know, differentiate between the two. You can describe using the characteristic. This is head to head, and for pi bond, it's characterized by sideway. Sideway in terms of, look at my whiteboard. If I have a p orbital, when they say side to side, this means I'll have another pi bond sigma, and the shared electrons will reside here. You see where the electrons, they overlap side by side in a state of head to head. So I meant to have opposite spin for the electrons. There is an overlap. It doesn't show clearly here on this diagram, but have in your mind that there are 2 p orbitals overlapping sideways. This is head to head. That this is head to head. That the p orbital are coming to overlap head to head, and the sideway for pi bond, which is a triple bond. That's what you need to know in terms of describing characteristics of pi bond and sigma bond. This is a detailed pictorial representation of double bond and triple bond. Double bond and triple bond. This is the description on how you end up with a double bond, with a triple bond. If you look at the bottom picture, in both cases, there is a single bond here, and there are 2. All right, and there is 1. All right, there is 1 pi bond. So in other words, what you need to take home from this slide is a double bond. All right, double bond consists of 1 sigma, all right, and 1 pi bond, there is one pi bond and one sigma bond in a double. All right. Don't let that slide out of your way, that you forget how to interpret a double bond consists of one sigma. The purple color here stands for sigma. You see there's an overlap head to head. And then sideways for pi bond, there is the sideways. So this consists of, or this makes up what we call a double bond, which you already know what a double bond is. When we get to a triple bond, that means 3 lines from chapter 8, that's a triple bond. Just be sure, triple bond. The bottom line, I mean the bottom diagram here, if you look in between along, you can see there is a single bond. So here, it consists of one sigma bond, or one single bond, all right? One single bond, sigma bond, and 2 pi bonds. This is what makes up the triple bond. If you look at the lines of the purple here, there is one below and there is one above it, but here we only had, one for side overlap. So the 2 pi bonds you see here, this is 1, this is 2, and the single one is in here. This is what I want you to take home from this slide. What makes up the triple bond? What makes up the double bond? For multiple bonds, there is one sigma bond, and the rest are what? The rest are pi bond. There is one sigma and one pi bond for double bond. In triple bond, there is one sigma and there are 2 pi bonds. We can't go beyond that. I'm not going to ask you questions beyond, knowing what constitutes a double bond and the triple bond from the sigma and the pi bond explanation. All right, in the shared electron, we say that those are localized electrons. Bonding electrons are said to be localized, the rest are delocalized. Those are 2 types of electrons, just the way we talked about in chapter 8, bonding electrons and non-bonding. You draw the Lewis structure of a molecule or polyatomic ion, and then you have to distribute, whatever it remains. Those unpaired or unshared electrons with the represented pi dots are being referred here as delocalized, where the shared one are localized electron. If I go back one slide on my whiteboard, I can say that these are the localized, the shared one. The shared one, the unshared one are localized. Well, this is just, benzene. I don't want to go in details on how the delocalization of electron, you will go in details in organic. So last, any question on section 9.6? You got to read again on multiple bonds. Let's move forward to section 9.7, molecular orbital theory. Remember valence bond theory about overlap. Molecular orbital theory is formed when atomic orbitals, combine in a molecule. MO stand for molecular orbitals, have almost same characteristics as atomic orbital. Let's just start and understand what this atomic orbital means. If we are referring to hydrogen, for example, electron configuration look like this. It's just one hydrogen. This is atomic orbital. If I have helium, with 2 electrons with opposite spin, these are atomic orbitals. When you look at lithium, for example, there is one S, this is one S, this is one S, and there is a 2s for lithium with 1 electron. These are atomic orbitals. To understand molecular orbital, we have to go back to the special type of electron configuration where you use up and down arrow to represent electrons, and lines, small lines, represent what we call atomic orbital. In molecular orbital, I'm just going to show you how to construct molecular orbitals for a molecule, right? When we say molecular, you remember molecules? Molecules are made up of non-metals. And this is a molecule. This is a molecule. This is a molecule. This is a molecule. All right, this is a molecule. Let's to give you a few examples of what we mean by molecule. When these two combine, or two of chlorine, two of oxygen and bromine, the electron reside in what we call molecular orbital. And they have the same energy. You can visualize this electron density of contours using the diagram, I'll show you the diagram later. And just to give you the description of atomic orbital versus molecular orbital, which we will see later on. When two atomic orbitals overlap, two molecular orbitals are formed and so forth. We have what we call one bonding and one antibonding. Let me explain what this bonding and antibonding means. If in hydrogen gas, this is hydrogen gas, right? This is hydrogen gas, and in hydrogen gas, in chapter 8, this is how you represented that with a single line. In molecular orbital, if this is a hydrogen, all right, if this is a hydrogen here, 1s, and then another hydrogen here with 1s, they will combine to form, if this is electron, let's say that is an electron in here, they will form one molecular orbital with each electron coming from each hydrogen. This is H2 now, and the two here, we call this molecular orbital. So when you look at the molecular orbital, you have an atom on this side and an atom on this side, and they form the what we call molecular orbital with this term here, bonding and antibonding. All right, bonding and antibonding. I want you to learn how to construct, if we start from here, say 1s, 2s, and then 2p, like that. This has one what? This has one line, this has one line, this has, let's say this is an orbital. Let's use these boxes right here. Maybe it's gonna look clear. And P has 3 orbitals, remember that? And here, if I have 1s with 2s with 1 orbital, and then 2p with 3 orbitals like that. Molecular orbitals will be here. This is atomic orbital, AO for atomic orbital. This is AO for atomic orbital. And here is molecular orbital, MO for molecular orbital. How do you write the molecular orbital? How do you, just the way we write 1s2, 2s2, 2p6, 3s2, and the same way you will learn how to draw the molecular orbital until you commit to your memory. Just the way you do 1s2, 2s2, it's the same thing. And this is how it goes, that it's gonna form these two here, will form one molecular orbital. All right, these two will form one molecular orbital. All right, this will form also another molecular orbital. But the 3 here will follow this from here. And we name them 1, and then there are 2, and then there are 2, and then there are 2, and then there are what? There are 2. Here we have 2 of them. We have 2 of them. 2 of them. Just, you know, they are combining. Give you that. Give you that. This comes, give you that. If you count this 1, 2, 3 right here, 1, 2, 3, and then 1, 2, 3. How many total? If we are mixing the 2p, we should end up with 6. 1, 2, 3, 4, 5. Yeah, I had an extra one here, so this should be 1 right there. For 1s, 1s you end up with 2 orbitals. These 2s you end up with 2 because 1 and 1 gives you 2 here. 1 and 1 give you 2 here. 3 and 3 gives you 6. If you look at the 2p, I have 2 boxes next to each other. I have 2 boxes, and then there is 1 piloid, and then there is 1 piloid. If you look at this, if you split it into 2 even, you will have what at the top right here. This is what we call bonding, just to explain what is in here on the PowerPoint slide, that bonding orbitals are constructive, destructive, one bonding and antibonding. So here are the bonding, we call this bonding orbitals. So for everyone, this is the bonding orbital, this is anti-bonding orbital, this is bonding, this is anti-bonding. Tell you what they represent for when you draw the molecular orbital. So learn how to generate this. It might not look clear, but in the subsequent slide, you will see clearly how to write or draw the molecular orbital, Once you figure it out, you don't even need to, you know, to start from scratch here. You don't need to start from scratch here. Just the way, you know, when I was drawing the line like the zigzag like this, you don't have to do that if you know how to write 1s2, 2s2, you know, and so forth. Once you figure it out, once you commit to your memory, then you just have to draw this and fill in with the electrons, This is just a simple or the simplest form of molecular orbital, where there is one antibonding and one bonding, one antibonding and one bonding orbital, molecular orbital. This MO on my whiteboard here, MO stand for this. I have the bonding, we call this bonding, and we call this, you know, and the bonding at the top right here, and the bonding right here, we have it. It's shown with the asterisk star. Please take note of those notation here, star, because question will be given probably in the exam or quiz, and they represent, or you should understand that a star represent antibonding. Look, the antibonding orbital in molecular orbitals represent antibonding. Just the regular sigma or pi represent, you know, bonding electrons. So this is for hydrogen. And for hydrogen gas, the 2 electrons, 1 electron is coming from each hydrogen, will reside in this bonding molecular orbital. If we add more electrons for other molecules, and then we will continue filling in this molecular orbital diagram. We call this molecular orbital diagram. We fill in with valence electron. Remember, we're just looking at all the electron in an atom. We use the molecular orbital diagram to determine what we call the bonding order of a molecule. And bonding order just tell you how many bonds are in a molecule. How you end up with this molecular orbital diagram? On my whiteboard, I'll start by saying for hydrogen and for another hydrogen here, if this is 1s with 1 electron, if this is 1s with 1 electron, remember we end up with 2 molecular orbitals. It's just gonna give you 2. It's just gonna give you 2. Each electron from each hydrogen doesn't really matter. You have to fill in just the way you write the orbital filigree. Remember the degenerate, you put electron first like that before you start pairing them up. Exactly, you do the same thing. You bring the electron in here. Let me just use the blue one. This electron is coming from the right hydrogen here. And then the red one, all right, the red one will just come, and they should have opposite spin, by the way. They should have opposite spin. They should have opposite spin. So that's how you write the molecular orbital. So if I have something else, that's what you fill in there. In order to determine how many bonds they are formed, we use what we call bond order. Just abbreviated PO for bond order is given by a half of number of electrons in the bonding, or bonding electrons, half of bonding electrons, all right, minus antibonding electron, and the bonding electron, and the bonding electrons. So if you look at the molecular orbital diagram, 1 electron from each hydrogen, they all occupy the lowest. This is the bonding. We don't see anything on the antibonding, and please take note of this star, sigma star, 1s sigma star, 1s just sigma. This is the bonding. If you don't indicate that, you will mess up with the calculation of the number of bonding and electron and non-bonding electrons. Electron occupying the top parts are said to be antibonding, and you count how many of them, not how many pairs. So in this equation is half of 2, we have 2 electrons down here, minus 0, we don't have anything here. And this bond order, it tells us that it forms 1 bond. It forms 1 bond. So with that, you should be able to see what is meant by, you should be able to understand what is meant by bonding and antibonding electron in order to determine the bonding order for electron bonding order. Let's see, now the plot for helium. Helium is number 2 on the periodic table. And if you try to just determine the bond order, writing the molecular or drawing the molecular orbital diagram, 2 electrons from each helium atom to form the molecule. They pair them. One is coming from this, it's going to come down here. The other one is coming from this, going to go here. The other one goes up here, and the other one goes there, they bond. So if we calculate the bond order, MPO, half of 2, these 2 right here, minus 2, which right here, which is 0. What does it tell us? It tells us that, you can have a molecule with no bond. This is impossible. There's no way you say that, helium with the atomic molecule or the atomic atom or with 2 atoms exist, which makes sense because we know group 8, they don't react except maybe few. It's beyond our scope. Bond order tells us that there is no bond, which means there is no molecules. This molecule will not exist. So up to this point, you should have a sense on how to calculate the bond order, or why do we have to determine how many bonds are formed. There are, these are just rule or guiding principle for drawing the molecular orbitals. Number of orbitals formed equals to the number of atomic orbitals. Look here. How many total atomic orbitals for hydrogen gas? 1 plus 1 is 2, so we end up with 2. If we have 3, then we end up with 3. If we have 4, we end up with 4. Atomic orbitals combine with atomic orbitals of similar energy. In other words, you cannot have 1s combining with 2s. No, they shall have same energy. Shall have same energy. You should not here recall Pauli's exclusive principle. When you put electron in the same orbital, they should have opposite spin. Opposite spin, it cannot have parallel spin. And when you have degenerate orbitals, they are singly occupied first before you start pairing them up. What that means is if I have the 2p here, 2p, all right, 2p like that, and 2p on this side, I should end up with 6 molecular orbital, 2 there, 2 there, 2 there, 2 there, and then 1 at the top. That's how you combine the atomic orbital. What is meant by singly right here? When molecular orbitals of the same energy are populated, 1 electron enters each orbital, same spin before you pair them up. So if I'm putting electron here, I'll just say 1 there and then 1 there. Before you go back and pair them up, this was Hans' rule. You say that these are degenerate. These two right here are degenerate molecular orbitals. Degenerate means they have the same energy. Go back again, you can read that, but with practice, you should be able to look at the construction or drawing of molecular orbitals. The other, gave us an example on lithium being diatomic, 2 lithium combining. If we draw the Lewis, not the Lewis, but atomic orbital for each lithium atom, we call these atomic orbitals, molecular orbitals. We don't need 2p. If in atomic orbitals, of course, all the way to 2p here, goes all the way to 2p, and then you'll have to come up with something similar to what I have on my whiteboard right here. You'll have to come up so that you fill with those electrons. So if I'm doing for lithium, 1 electron will come here, 1 electron will come here. 1 electron will go up here, 1 electron will go here. This is coming from 1s. And then 1 electron will come down here, 1 electron will come down here. They occupy the lowest fast before you feel the bonding. It's a rule of thumb. You cannot say, let me take these 2 up here and then take these 2. No, it doesn't work like that. You occupy the bonding fast, the sigma, without no star. You have that. If we calculate the bond order, all right, bond order, using this to help you out on how to calculate the bond order, this will cancel out. The 2 will cancel out. What we use is the topmost part here, which is a half times 2 minus 0. The 2 electrons right here. If you use the total, that's fine. It's just gonna come out. If you say bonding here, 2 plus 2 is 4. This is bonding, this is bonding. 2 plus 2 is 4, minus 2 is 2, which is the same thing. So you can assume that this will cancel out with that, and we only focus on this. And this is 1, which means there is only a single bond on Li or lithium, Li or lithium. And true, it exists at high temperature, Li2 exists. Taking to the next level now, you don't see in this diagram, you don't see 1s on the atomic orbitals. You don't see 1s on atomic orbital, but just going to the second shell, the 2s and the 2p on the second energy level. These are the molecular orbital. I recommend learning how having your 1s here and having 1s here, because it's just gonna work for all the atoms you will be dealing with. Just like before, and the bonding will be always at the top with the star star. These are at the bonding molecular orbital. These are bonding molecular orbitals. We call these atomic orbitals. These are just, we can just, if we have electrons right here, 2 electrons, 2 electrons, then one will come from each atom, and then you feel it that way. This is what I was saying earlier. You get to be able to draw the molecular orbital diagram. This is called molecular orbital diagram. If you can reproduce this and label them as sigma and sigma star, pi and pi star, and sigma star, then you're good for the rest of chapter 9. For the remaining of chapter 9, we'll talk about, paramagnetic and diamagnetic, which will come, we will look at it later on. So this is a molecular orbital diagram, molecular orbital diagram, molecular orbital diagram, molecular orbital diagrams. You don't see atomic orbitals. You don't see atomic orbitals on either side. What you see on the next slide is just this portion of the molecular orbital diagram. And if you look at the beryllium, all right, beryllium is in, beryllium is number 4, right? Which means beryllium is number 4, which means beryllium is number 4. And if I have 2 berylliums, that means I have what? 8 electrons in total, 8 electrons in total. What has been cut off here is the 1s. I recommend building from scratch. The other is just, abbreviating some stuff here. You don't see the 1s. So if I have beryllium, let's see beryllium, for example. If I have beryllium here, let's see beryllium, and I have another beryllium on this side. Beryllium, there is 1 electron here, 2 electrons. This is 1s, 1s, 2s with 4 electrons. If I have 1s here with 2 electrons, and then 2s with the 2 electrons right there. Write the electron configuration. I'm just writing electron configuration on this side. And then atomic orbitals, remember the total number of molecular orbitals equals to the sum of atomic. The total number of molecular orbitals here equals to sum of atomic orbitals. So here I'll have 2, and you should know that these are antibonding and bonding. So I'm gonna have here 2, all right? I'm gonna have here two orbitals like that. What I want to show you is how you feel that with electrons. If one is coming from this, the other one is coming from here. This and that. So we take care of that. The two electrons here is, all right, the two electrons and like that. Now, it should have a different color. You should have a different color. Let's say different color here. 4. So here and here. If you look at the electron, total number of electrons, 2 plus 2 is 4, and we have 4 right here. I was writing beryllium Pe, and you don't see that. This is for Pe. And does it really exist? You can calculate the bond order and see how it's gonna work. If it's 0, that means it does not exist. Let me show you the first one here for boron. Boron is number 5. This is number 5. And if we have P like that, P2, that means this is 5 electrons. This has 10 what? 10 electrons. 10 electrons. You write for each, all right? You'll write for each boron, half for each boron here, maybe use a different color there. This is 1s, 2s, and 2p on this side, 2p on that side, 1s, maybe I should have used a different color here, maybe use a different color so that you can see how that is 1s, that is 2p, that is 2s, and then 2p here is 3 of them there, 3 of them there. So if I fill in with the electrons, this has 5, 1, 2, 3, 4, 5, for atomic number 5. I'll do the same thing for this. This is 1, 2, 3, 4, 5. And if I do the now the molecular orbital, these are atomic orbitals, atomic orbitals, atomic orbitals. This will give me 2 orbitals, so I'm gonna have 1 there, I'm gonna have 1 there, I'm gonna have 1 there, I'm gonna have 1 there. This is coming from this to right here. This is coming from this to right there. This is coming from this right there. You have to indicate. When we get to 2p here, 2p and 2p right there, we will have 1, we'll have 2, all right? Should have enough to give me space to write the electrons. And then another 2 right there, and then the other one right there. This is from 2p, this is from 2p. And remember to indicate the star here, you indicate the star. You have to know where they are. So if you fill in with the electron, remember we should account for 10 electrons. Account for 10 electrons. So if I have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, 9. 10. The 2s, 2p, 10 electrons, each from the 1s and the 2p, and the bonding and bonding electron, bonding and the bonding electrons. Oxygen, that's the same thing, 2B. You don't see the 2S. So if you have to calculate the, the bond order for each one of them, there are two bonding, 4 minus 2, you end up with 2. The bonding here is 6 minus 2 divided by 2. You end up with 4. This will not exist because of the bonding electron. Because of the bonding electrons being the same, they will cancel each other and give you the bond angle. So the point here is to draw the orbital filling diagram, the molecular orbital diagram, and fill in the atoms, fill in the electrons from the atomic orbitals, let's see, the highest energy occupied, by molecular orbital in F2, that is fluorine molecule, is what? Unless you draw the molecular orbital diagram and fill in with the electron, you won't be able to see, all right, you won't be able to see where the electron reside. So let me go back to help you with this. You will draw the orbital, all right, you will draw the molecular orbital diagram, and for fluorine, F2, all right, remember this is S2, there is 1s1 here. Let's count the number of electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all right? 14 electrons, 14 electrons. So you'll just fill in the molecular orbital the way you do, all right? You just fill in the way you fill the molecular orbital diagram, starting from, from the lowest, accounting for the total number of electrons. F2, remember fluorine is in group 7, and F2, this has 14 electrons, which are represented by these lines, up and down, up and down. They are just going sequentially from the lowest to right there. So the question here is the highest energy level. This, as you go up, the energy level increase. And if I look, it corresponds to 2 pi star, which is the bonding right here, and the bonding for that. That's how you write or determine the highest, and the correct answer for this is D. So if it is in a quiz or exam, somebody will say, how will I know which one is which here? They all look alike, like this look like this, and look like that. And so what is the difference between this? It comes down to understanding the order in which, and I believe there is a typo here. This should be 1S. Let me check on my text real quick. This should be 1S. To be clear, that should be 1S, all right? That should be 1S, 2S, all right? That should be 1S, 2S, 2, all right? This should be 1S, to give you that, 2S, and then 2P. You go in there like that and give you the electrons you have in there. So unless you identify by bonding and unbonding, all right, sigma star and sigma, they make a difference. Any question on molecular orbital? Any question on molecular orbital? I know you can do that. Please read on the relevant section so that when you are asked about the molecular orbital, you should be able to look at that. Same question on molecular orbital is based on the molecular orbital theory, the bond order for nitrogen to nitrogen, that is N2, all right? N2 is what? We got to draw that, you gotta draw for nitrogen, you will draw the molecular orbital field in, and if you look at the bonding, I see that the bonding here, we have 6. Anything on star, I don't see anything. So if I was to do that on the whiteboard, it will be now a half of 6, because I have 6 electrons here on the 2p. 1, 2, 3, these are the bonding, minus 0, and this gives you 3. This is the bond order. Instead of just memorizing, suppose I give you something else, you should be able to determine the correct answer for that is C. C. So when it comes to bond order, remember the only way you can do that, you can answer that question is to draw the molecular orbital filling diagram, fill with the electrons, use the equation. Bonding order is half of bonding electrons, that is certain number of bonding electrons minus certain number of antibonding electrons. Bonding electrons are those electrons with no star on the molecular orbital. Antibonding electrons are those electrons residing on the orbitals with a star, with an asterisk. And plugging in the equation, you end up with that. And the bond order is 0. Bond order is 0. Any question? Aaron, question? Cook, question? Are you there? Jonathan, any question? Somebody out there say yes, no? You have a question, Aaron? No question. Thank you, Stephanie. No. Let's shift gears to paramagnetism and diamagnetism. When we say something is diamagnetic, that means it's not attracted towards the magnet. This is my stylus pen. If I have a magnet and try to pick it up using the magnet, it's not gonna, be attracted. It's not gonna form, we say it's diamagnetic, it's not attracted. Paramagnetic molecule means it is attracted to by the magnet. And looking from the, what we just talked about, a diamagnetic molecule has unpaired electrons. No, paramagnetic has unpaired, so while diamagnetic has, or all electrons in molecular orbital diagram are paired. Paramagnetic molecule has unpaired. This one has unpaired. So if we go back to this diagram, I can say this is paramagnetic because I see they are unpaired. This is diamagnetic. All of them, they are paired up. This will be attracted in the magnetic field. This is diamagnetic. This is paramagnetic because there is what? I see 2, all right, I see 2 unpaired electrons. I can say this is paramagnetic, all right? This is paramagnetic, no, this is diamagnetic. All of the electrons in the molecular orbitals are paired. This is diamagnetic if it exists, but it looks like it does not exist because we have a bond order of 0. But nevertheless, looking at the unpaired electrons, all of them are paired, and we say that the molecule is paramagnetic. Question on paramagnetism is, it is anchored on molecular orbital diagram. You have to draw that, see which molecule has or which atom or ion has paired or unpaired. If there is unpaired, then you say it's paramagnetic. Here is an example, oxygen, all right? When we say O2, let's say O2, right? O2, oxygen is in group 6. So this has 12. 12 what? 12 electrons. Oxygen is in it's number what? Number 8, right? Number 8. And 8 plus 8, this has 16, this has 8. These are number of electrons. These are number of electrons. If we fill in the orbital filling diagram for that, right here, I'll just go back to that. This is for oxygen. Let's see, for oxygen, for 16 electrons. If I write the 16 electrons here, remember the 1s will give our start, the 2s will give our start, and that, this is the 2s, this is the 1s. And then the 2p will give us this, and the 2 there, the 2, and the 2, and the 1 right there. This is the 2p. So for 16 electrons, so if I fill in with the 16 electron for oxygen, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, this is 1, and then 16 right there. These are unpaired, all right, unpaired electron. This is unpaired electrons, which means oxygen is paramagnetic. You cannot memorize and say, let me memorize this and say it's paramagnetic. No, 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 no. You have to draw this and see all the way up there until you end up with unpaired electrons, unpaired electrons. You're gonna have that. We say oxygen is paramagnetic and it is attracted towards if you look at this, we have 1, 2, and shared electron. It is paramagnetic. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They don't show you the 1s down here. They don't show you the 1s. When it comes to ion, I know we have just been looking at the neutral atom. Suppose you are given, how are you going to handle the molecules with overall charge? Recall, extra negative indicate an extra electron. An overall charge or positive means we are less by electron. So A, all right, in A, in that case, this has 18 electrons. So if I'm 18 electron, I'm just gonna pair them up here and make this one diamagnetic. For this, you know, neon is number 10, it has 10 electrons. So 2 neons have 20, a total of 20. So for B, N2, Ne2, sorry, has 20 plus, no, 20 minus, you subtract that, all right, you subtract 2 electrons and you are working with 18 electrons. In filling this diagram right here, in filling this diagram, you will work with 18 electrons, you will work with 18 electrons for something like that. For something like this, we had, for O2, this has 16 electrons, right? But O2, with an overall charge of plus 2, it's gonna be 16 minus 2, all right? 16 minus 2, you work with 14 what? You work with 14 electrons. 14 electrons. In filling this diagram right here, in filling this diagram, and see which one will give you, you know, single or unpaired electron for you to determine which one is paramagnetic, which one is diamagnetic, which one is paramagnetic, which one is diamagnetic. It's the same thing, okay? So this is what happened for oxygen, that it's attracted towards a magnet. You pour liquid oxygen through some strong magnet. You see the magnet, it's not gonna go through. You don't see anything going through because they are attracted towards a magnet. They are paramagnetic. That's what is meant by that. With that, that marks the end of chapter 9. Same thing for heteromolecule. Hetero means different atoms forming a molecule, such as such as CO, all right, such as NO, all right, such as, yes, diamagnetic, paramagnetic is same thing. If you have a unpaired electron, this molecule is said to be paramagnetic. Yes, one. That marks the end of chapter 9. That marks the end of chapter 9. I'll make homework assignment for chapter 9 available, and also the quiz to help you for the upcoming exam. And as you prepare for final, okay? As you prepare for final, I recommend that you use the study guide from midterm exam, from the quizzes, and you should do well. I still will send out the study guide for final. But to be ahead of the game, I will print out study guide for the quizzes and use a check mark that I'm familiar with this. I know this. Which area do I need to revisit? Which area do I need to focus on? All right. That will help you in preparing for the exam. With that, that marks the end of chapter 9. I want to shift gears to chapter 10. If there is no question on 9, I'll shift gears to 10. And this is a straightforward chapter, something you covered in Introduction to Chemistry. All right. Recall gases or in state of matter. Gas is one of the state of matter you have seen before, the properties of gases. And in this chapter, we will focus on one of the 3 states of matter. Okay, this is what what I intend to go through in chapter 10, characteristics of gases. Gonna talk about the pressure, the gas laws. I look at the gas laws there. We're not going to look at all the gas laws, but just few. And just spend more time on ideal gas law, because this is what you will need in the first experiment for Chem to revolve around the ideal gas law. Mixtures, all right, and partial pressures. Last, we'll see the real gases versus the ideal gas. Gonna talk about that. Let's start off with characteristics of gases. You all know properties of gases compared to solids and liquid. Most of the gases or all gases, they have almost similar properties. Let's talk about their compressibility. They are compressible compared to solids and liquids. They can expand to fill the container it contains, right? They are highly compressible because of the large intermolecular space. If this is a gas atom. If this is an atom, they have large spaces. I can compress because of this. But for solid, you cannot compress solids because, you know, they are, the molecules are in a fixed position. They have extremely low densities compared to solids and liquids. Solids and liquids densities are expressed in grams per ml or grams per centimeter cubic, but for gases, they are expressed in grams per liter. They have extremely low density, so to get a meaningful number, you work with liters. They can mix homogeneously without, reacting. Two or more gases can homogeneously mix. That means they don't react. For example, in the air, there is nitrogen gas, there is hydrogen gas, there is CO2 gas. All those, they don't react, but they just form a homogeneous mixture. Very few properties of just common gases here. You can read on your own, familiarize yourself. Few examples of, gases out there. Okay. What I want you to know is just a general one I took in the previous slide right here. This is what I want you to learn in comparison to those of solid and gases. Properties which define gases, which we will see later on in gas laws, are temperature, pressure, volume, and N. For their number of moles, we will designate that using N, all right? N stands for the number of moles of gas, and having all seen this, gas laws are derived using the four identities you see here. We'll see later on, firing one or two or maybe even three can affect a property over a gas. But before we look at the gas laws, let's look at the concept of pressure. I know you covered this when we talk about pressure. Okay, pressure over gas is simply the force of force exerted by gas molecule on any surface, and it is determined by we know the force and the area being exerted. We talk about the pressure over gas. It is simply the amount of force exerted on a given area, force over area. Of importance is the atmospheric pressure. It's just the pressure exerted on the surface by a column of gas, all right? When we talk about atmospheric pressure, the pressure or the gas molecule in the atmosphere exert pressure on any object on the surface. We call that atmospheric pressure. I would ask you about, the values we get there. The most important thing is, how do we change unit of pressure from one unit to another unit using the dimensional analysis? These are different units used to express atmospheric pressure. And the diagram you see here illustrates how the first scientist we call Evangelista Torricelli in around 16th century, he took a long column. This is a glass tube with a closed end, completely filled with liquid mercury, and infert it on a container with liquid mercury. So we have mercury here, and the mercury inside this glass column, it was completely filled, that there was no space, there was no vacuum here, and then it just invited in there. And starts out that the liquid mercury dropped to a certain height from the surface of the liquid mercury in the container to somewhere where the meniscus was. You see this height right here? At sea level, at sea level, look at my whiteboard, at sea level, H on the diagram equals to 760. In case you have been wondering where the 760 you have been using in pressure conversion came from, it is coming from here. The distance from the surface to the meniscus is 760 millimeters, and you see millimeter mercury here, it has to do with the liquid, all right? liquid mercury in the barometer. All right, barometer is just an instrument used to measure what? Used to measure the atmospheric pressure. Barometer is an instrument used to measure atmospheric pressure. He invented that, and when he did this at sea level, this was the distance, this was the height, and we have been using that as the sea level. Of course, if we take this to different place with a different altitude, the height will change based on the atmospheric pressure. So what is holding this liquid mercury here from just pouring in here is the pressure right here. It's the pressure from the atmosphere, In honor of Evangelista Torresoli, he is, credited for, this is just coined. The unit you see here, TORR, is coined from his last name. All right, you see in the reading the text, Torresoli is his last name. Evangelista Torresoli was a French scientist who came up or who discovered the barometer. And 1 atmospheric pressure equals 762 torrs equals to 760 millimeter. Mercury equals to 14.7 pounds per square inch, was 29.92 inches and so forth. This is a large equivalent statement I'll give you in the exam. Yours is to use in changing pressure from one unit to the other unit. For example, here, using dimensional analysis, 0.500, and this is 3 significant figures, atmospheric pressure is the same as how many millimeter mercury. So using dimensional analysis, 0.500, you want to get rid of millimeter mercury. This is your conversion factor. You want to get rid of atmospheric pressure. You are looking for what? Millimeter mercury here, millimeter mercury. The numbers will be derived. You have to generate from the equivalent statement here that 1 ATM equals to 760 millimeter mercury, and unit cancellation. You end up with that. Looking for my calculator, you just plug in your calculator, 0.50 times 760, and this is 380, 380. This is for this question, 380 millimeter mercury. You got to show your work and write with the correct units. That's the units we are looking for. With that, if it was PSI, you use the appropriate equivalent statement. If it is PSI, this is what's going to happen. If I'm looking for PSI, I'll say ATM times, if I'm looking for pounds per square inch, I want to get rid of ATM. 1 ATM is the same as 14.7 PSI. That's what it means. If it is inches mercury, you'll do the same thing. If it is kilopascals, you'll do the same thing. Just remember, using dimensional analysis, you can do that. That's how to, convert pressure from one unit to the other unit. Now, we looked at in the previous slide, the instrument used to measure atmospheric pressure we call a barometer. This is called a barometer right here. Might look different from another text, but for a sample of a gas, we use what we call a manometer. Manometer is an instrument used to measure pressure of a sample of a gas. This is a sample of a gas, and the construction of a manometer look like this. It has a U-shaped. It has a U-shaped, arm hooked up to the container of a gas, if you open the valve here, depending on the pressure of a gas inside the manometer, common sense, look, common sense, if the pressure is so high here, it will push this liquid mercury here, and it will rise up there. If the pressure is so low, then the atmospheric pressure will just push the liquid mercury on this, and it's not gonna go all the way, but this height on the other side of the U-shape will change depending on the gas pressure here. One end is open to the atmospheric pressure, you can understand that. Now, the equation here is, let's say high pressure. For high pressure of a sample of a gas, how are you going to calculate? Pressure of a gas is obtained by using this equation. P of the atmospheric pressure plus H. What is H? This height here. We can know the difference between the, this height right here. Sometimes you may be given. Sometimes you may have to calculate. For example, this height right here is the difference between this lower here and the height here. To get the height, 136.4 minus 103.8 will give us height. And if we want to find the pressure of this gas, it's just pressure of the atmospheric. If this is 760, then we say 760 plus the height here in millimeter mercury. And of course, the height here, the units is in atmospheres. You can change now to millimeters mercury. If it is 1 atmosphere, if it is 1.2, if it is 0.9, change to millimeter mercury so that you add to the same what? Same units to get the atmospheric pressure. Atmospheric pressure, okay. If the pressure is low pressure, all right, low pressure, pressure of a gas, like that, is given by P of the atmosphere. This does not mean pressure in atmospheres, pressure of the atmosphere, which can be in any unit. In this case, because the height will be in millimeter mercury, we'll have to work with millimeter mercury. If it is centimeters, and then that could be centimeter. Minus H. That means the height here on will be higher than what you have on that. These two equations here helps you to determine the gas pressure using a manometer. It is good to understand how this works. I have a YouTube explaining, I don't want to play right now because of time factor, how to calculate this explanation in details on how to calculate pressure of a sample of a gas inside or using a manometer. It's just similar to this. Let's solve the example here. If the pressure of a gas inside the flask, which is this one right here, were increased and the height of the column in the open end went up by 5.5 millimeter mercury, what will be the new pressure in a gas? It's assumed that this problem right here, it was given, it is atmospheric pressure. You'll be given that pressure, you'll be given more information. This was a continuation of problem 10.2 on page 423. This was 760 millimeter mercury. This is the atmospheric pressure. This is the PATM, atmospheric pressure. The question is, if the pressure here is increased in such a way that the height in the open arm, so this will increase because the pressure is increased, it's gonna push this. and this will go up. So if the pressure here is increasing, it's gonna push this down, and that means it will come down right here. This level right here will go down here, and this one will go up. Remember this, it went up by 5, so it will go up by 5, which means the new one will be, or the top one will be 136 point what? 4 millimeter plus 5.0 millimeter. It went up by 5. The other one will go down because it is being pushed. It will be 103 point what? 103.8 millimeter minus 5.0 millimeter. Why am I doing this? It's because if the pressure is increased, look here. Pressure of a gas inside the flask will increase, and the height of the column. If this one is going up by 5, this one must be coming also down by 5 because the pressure is increasing. That's why I'm doing that. In order to get the, this will be, in order to get the height, all right, in order to get the height, 136.4 plus 5. So this is 141. This is 141.4 millimeter, and 103.8 minus 5. I see it is 98.8. So instead of this, to get the height here, my new value on the low end will be 98. It will come down further because the pressure increase. This will go up to 141, and the difference between the two now is 142. Height is the difference between the two, 141.4 minus 98.8. I see 42.6 millimeter. And since the pressure is increasing, you have to understand here that for high pressure, you add the height. For low pressure, you subtract the height. So the key here is find the value for H first, and if the pressure is low, you subtract. If the pressure is high, you add the value to the atmospheric pressure you will be given. For this problem, like I said, it was given as 760. So we will add 42.6 to 760 millimeter mercury, which was atmospheric pressure. All right, 42.6 plus 760 millimeter mercury, and this is 802. For this problem, it is 802.6 millimeter mercury. This is the pressure of the gas inside the manometer. It might not be complicated as the way I have in this problem. They might just only give you the height, and it's easier for you. Is it the pressure is high inside the manometer, or is it low? And then you use the appropriate equation here. Is the pressure high? If it's high, and then you add height. If the pressure is low, then please watch on this for more explanation. I have the PowerPoint slides posted online. Watch on that YouTube so that you understand fully how to answer question on manometer. That is determination of pressure of a sample of a gas inside a closed container, a manometer in that case. Let's go back to the standard temperature pressure. I know before in introduction to chemistry, I know what is meant by STP, standard temperature pressure. This is not the stuff you add on the gasoline car when your car starts smoking, like giving smoke. There's some stuff some folks add, and there the label is STP. That's not what we are referring to here. It stands for STP, not S. It should be like this. I need my coffee. It should be STP for standard temperature pressure. When you are at standard temperature pressure, temperature is 298. All right, 298 Kelvin. Pressure is 1 atm, and we know 1 atmosphere is the same as 760 millimeter mercury. And not for this chapter, the concentration is always, 1 molar concentration, molarity concentration. This is concentration, just to give you what is meant by, condition at STP. This can be 760 millimeter mercury. Where am I getting 298? I hope I didn't throw anybody off by just plugging in a number from somewhere. This is the same as 225 degrees Celsius plus 273. You know that. I know you know that. Some stuff, you are expected to know. You are expected to know. All right. Any question? If there is no question, I want to stop here for today. I want you guys to work on the quiz, prepare for final. Like I said at the beginning of the lecture, final exam, it will not deviate from what you have seen before. All right. Significant figures, I'm just gonna ask you that. Do you know how to calculate the molarity of a solution? Do you know how to draw the Lewis structure of a molecule? Do you know how to determine the bond order and so forth? So use the study guide. I will not deviate from the same concept we worked with. I don't want to start the cast loss. I want us to start with a fresh mind, which will be our subject next Tuesday, all right? Tuesday, I think we have, there's an exam, right? So I want you to prepare. So there's no lecture next week. Just to be clear, from the course syllabi, I want you to really spend time. Next week, it will be the exam, and I expect you, just like the midterm exam number 1, exam number 2, and so forth, you will, all right, you will have the entire lecture session to take the exam. Otherwise, I'll make the exam available by midnight or 24 hours. I know we have all of them. Are we not taking the quiz? Yes, there is a quiz, Ronan Nicholson. Are we not taking the quiz on chapter 8? It has been available since last week. I'll make quiz number 9 available today, because I didn't want to give you quiz on 9 until you have that. It will be available next, all right, midterm. Yes, yeah, it has been available. Those have been available. So I just want to make sure, since I'll give you until next week. So I was assuming that you worked on 8, you worked on 9, because this has been available, and I think it's available by, it's available until tonight, 7 and 8. So I was assuming you have been working continuously. For 9, you have until your next week. You work also on that. So if I were you, I'd work on quizzes fast before I do the exam. All right. Any question? All right. If there is no question, I'll stop sharing my screen right now. Thank you for tuning in. Have a great weekend. Sanitize. Stay healthy, all right? Wear the mask and be safe. I'll see you again next time. Thank you and welcome again.